Our next presenter is Dave Quinn, who has worked as a consultant at Badleys for about 10 years in the role of project structural geologist and, not surprising, specializing in fault interpretation, fault seal analysis, and geomechanical fracture prediction. And he's going to give us a talk on that and on the T7 software business.
Okay, can you all hear me? I'm kind of lapelled up here because I tend to not be able to stand still. First of all, I'd like to thank the OGA, not just for inviting us today, but for also providing us with a free exhibition space downstairs so we can actually talk more about this afterwards. I mean, you know, I do a lot of the APGs and the SEGs and stuff, and if you knew what we paid for exhibition space, you'd probably get out of this business and into that one. So it's very, very much appreciated to get that for free and to get the opportunity to talk more. I'm going to try to cover a couple of topics that might sound a little bit diverse, but are actually, you know, very closely linked to the volume estimations that we do and the risk analysis that we do. And I'm going to start by doing something that I said I wouldn't ever do and show an equation, because if you weren't nodding off already. But hopefully that's one that we're all familiar with. And what I'd like to address is, in terms of the 30th round, especially when we're dealing with discoveries, a lot of this equation has been measured at least in one place in the reservoir, okay? You've got measurements from wells. The gross rock volume, yeah, you've got a thickness, and you can do your messing about with it to try and remove the smoothing that comes from both the nature of the seismic and time depth conversion and all the rest of it. But there's an uncertainty in here that will never get caught up in any simulator run that you do. And it's the uncertainty in the areal extent of the trap that you've created. When you create a map, and then you put that into the simulator, that's a systematic error. If that wrap is wrong, then everything that comes out of that simulator, doesn't matter how long you spend on it, doesn't matter what variables you put, it's going to be wrong. The map that goes in has to be right. And I'm going to show, hopefully, from some of these montages that the map really quite often isn't right. Nick showed this earlier, and he showed you what a montage looks like, and I think Gunther said there was 58 of them. I steadfastly downloaded all of them, but probably didn't need to, because I was about 4 in when I had enough material for the talk, and I'll probably cherry pick another couple as well, because there's a few strat ones here that we can't really do much with, but the structural ones certainly. So I'll start from the top with Freya and Fulla, which are kind of related. And just to get your bearings, this is clear. So, you know, infrastructure is pretty obvious here. We've got Fulla here and Freya down here. And I'll just look at Fulla first, which is apparently a stratigraphic pinch-out. So this you know, the strat pinch-out is the crest of the structure. I've seen in my time a lot of strat traps that became structural traps. Not so much the other way around. Okay, so especially when you look at this person's interpretation that they didn't even have the confidence to take that fault through, I would certainly be looking at it, because the dip closure follows a fault pretty well. And then these faults I don't like very much. But, you know, it's all done on 2D, so I can kind of forgive some of these odd geometries. But what I find even more interesting is the fact that Freya down here, which is in a lower reservoir, miraculously closes just before the block there, which is quite handy. Mother Nature's good like that sometimes. So here we're down in the clear group, and big old closure, big old potential here. But even within the same montage, somebody else tried to explain it in a different way. I don't like seeing faults appearing and disappearing. That's usually a red flag for me. So I would certainly be looking at this, because your gross rock volume is going to be very much dependent on whether that fault exists or not. But look, these are minor infractions, and like I say, 2D's tough to work with. Not so minor infractions are when we've got 3D data, really good data sometimes, and even some of the legacy stuff is perfectly adequate to do this. This is Catherine, and one of the anticipated steps are suggested steps. And by the way, when you look at these montages, if there's an anticipated step, I would take that as a suggestion, because the OGA are marking on structural interpretation. It's one of the things in your plea. And if it's not done, then I think you're probably going to be asked to do it. So here's Catherine, and I'm going to show you the original map and this map, because one of the anticipated steps is a fault seal analysis. And I'd like to do that right now for free using just a map. Right? You don't need to do fault seal analysis on this, because, okay, you might need to have a look at this fault and make sure it's a good closure. And I'm sure it is, because looking at the cross-section, there's a good juxtaposition seal. What I don't like is this, because that's probably a little terrace of data where there's a relay, and that could actually be a connection out of your reservoirs. That's the only thing I'd check about that. But let's get into the reservoir and imagine that I believe this crest, which or the closure here, which I kind of don't, and let's imagine that I believe this junction, which I definitely don't, but that I do believe it's all connected through there, even though the faults actually probably aren't very well imaged here. Well, that makes this the northern boundary of our trap. But this is 3,500 and this is 3,450. Each of those contours is 10 meters. So the displacement, I wager, at this point here and this point here is in the region of 1 to 1.5 meters, give or take. There's no fault there, right? That is not a fault. There's no seismic in the world will show you a 1 meter displacement fault. Somebody's drawn an arrow through here, a fault, on a map with absolutely no evidence for it. Like there might be something through there, there's a bit of disruption there, but it's not very big. So if that's not a fault, and it isn't, then surely we open up into here. So now this becomes our northern boundary. Like I hate this as well, this is just, yeah. But let's have a look at the contours here, and again, zero displacement. This compartment is completely connected to the one below it, as is this, as could be the whole thing, and I don't know what's north of here, but the whole thing could be connected. It's definitely not being segmented by 1 meter faults, like it's just poor mapping. This is the point. When you do your hydrocarbons in place estimation, it doesn't matter how long you spend in your reservoir, it doesn't matter what you tinker with. You can spend days in meetings giving out about the net to gross away from the well that you have. You're never going to get the right answer because there's your P100, right? There is an error that goes into all these things, and to think that uncertainty analysis is going to pull it out is just wrong. I'm going to skip blue sky. I just wanted to show you because I love the arrows. That's some great arrow work. I don't know what they mean, but anyway, when I see a contour map and it looks like it was left overnight and the slugs got in, that always worries me. Faults don't look like that, right? These are not what faults look like. You can go and you can touch them in the field if you wish, and you will never see them do this, all right? So I knew straight away when I saw this, I thought, right, we've got problems here, but I think sometimes people overgrid, or the systems overgrid faults so that they fit nicely into a simulator. And sometimes, actually, I've met structural geologists who said, oh, I had this really good fault, but they had to drop it out because it was just taking too long in the simulator. I'm like, oh, okay, all right. Just throw away the things you actually know in place of the things that you don't. That's good thinking. So I didn't like Dalziel from the start. And when I looked at this north-south line, you'd say, but Dave, what's wrong? Look, it's a nice little fault closure there. What I didn't like is that this obvious nick in the Zecht line wasn't pulled through. Somebody wasn't really thinking about their structure three-dimensionally. And this was very, very obvious in the east-west line. So here's Dalziel. I'm just going to blow up the important area here. There's the well, okay? This does not work. It doesn't work so badly that they couldn't even draw the fulmar in here, right? But if the pentland is connected to this antithetic-synthetic pair, then the pentland is more or less where my marker is. The whole point of an antithetic-synthetic pair is that there's zero displacement at the join. It's a hinge. It's not a through-going fault. So you can't have any displacement there. And if you put the pentland there, well, where are you putting the fulmar? It doesn't really make sense. So I don't like that. But if they had just seen this, and I don't know if this is the new seismic or the old seismic, there was something about reprocessing. I'd be a monkey's uncle if this wasn't in it. And somebody should have just drawn the fault in straight away from the start. And now you can see this is actually a completely different trap to the one that had been drawn. Now you can actually probably infer if this is an antithetic-synthetic pair, and I do believe this is an antithetic to this fault, then the displacement up here is going to be probably very little. In fact, using the same cycles, I'd probably put that one down there. But using the same cycles, now this is a structural model that works, and actually I'd probably take it to there. I'm not sure that the fault dies out there either. So what's the point, Dave? Well, the point is that they tested this. This is your hydrocarbons in place. This is the compartment that they tested. It could be that, it could even be that. But it definitely isn't that. So huge upsides in just doing the structural interpretation correctly. This is Bowmore. And if you've looked at it and gone, slugs, then good, my work here is done. Because once you see these faults, you just kind of go, oh, I don't know. And then you see the section and you go, I definitely know. That's really, really very questionable interpretation, I would say. I'm not going to labor the point too much. I think I've said enough about the standard of interpretation in these things. What I would like to say, look, I'll get to the point about why it's what we should be doing better, because it's very easy to pick faults, but pick problems. I honestly didn't mean that one. But yeah, it's actually easier to pick faults as well if you just know the rules. This is the thing, if you don't know the rules, then you can't be expected to break them. And people can actually be very good at picking faults on a seismic section, but not so good at correlating those seismic sections together to make a robust 3D mechanically sensible model, because they haven't been taught that skill generally. So it's difficult because sometimes, you come back with a problem and somebody says, well, a structural geologist didn't look at it. But a seismic interpreter is a structural geologist. The second you put a fault on a section, you are being a structural geologist. And if you don't understand how those carry through and link and meet, then you can't be held responsible, really, for creating models that don't make geometric sense. And the thing is, the software will allow you to do it. Software is dumb. Not only will it allow you to do it, it will encourage you to do it so that it fits easier in a simulator. It's madness. Anyway, I just thought, in the interest of the new technology thing, I thought I'd have a look at Ockley, which is in the Central Graben. And because it really reminded me of something that we published a couple of years ago for Maersk in the Danish Central Graben, which was a fracture analysis study, because nobody's done that on Ockley from what I saw. And the wells looked like they were really, they suffered from a lot of problems. I don't think this has been tested properly, but it's clearly conformable to structure, the AVOs and stuff, and it looks like there's a lot of volume there. What we did for Gorm is we made a fracture intensity map based on the strains that we saw. And if I kind of drag your attention into this upper area here, this is the well that they drilled after the fact. This is all published. We could give you the paper. And you can see here maybe the ticks in the background there, the orientations of the fractures that we predicted might be there. And they were, hopefully, good for flow. There's no point in picking sweet spots of fractures if they're slammed shut, right? A fracture slammed shut in the in-situ stress field of today has no business producing oil. What you want is the ones that are critically stressed. They're dilating. When you inject, they're the ones that are going to flow. So that's actually the fractures that you want to be hitting. That's what they hit. It was a known area of low matrix permeability, high fracture permeability, packed full of natural fractures. And it turns out to be, the savior of the field, really, in many ways, which is important. It looks like very complicated, high technology and all the rest of it. And the theory behind this is mind-boggling, right? But actually, all we've done, if I flip that image, kind of rotated around 90 degrees, all we've done is predict where there's a very well-developed relay zone. And well-developed relay zones are fractured to hell because that's the last thing that happened before they become one bigger fault. They start off as intact relay zones because the faults haven't overlapped very much. When they're only coming towards each other, they're quite intact. If you've got them in your field, then hydrocarbon's very, very happy to move through those. But here's the thing, how often do you get to interpret relays? How often are they properly interpreted? How often are they picked up? All faults have them, so do all of yours? And moreover, when you pick them, do they go in the simulator? I doubt it, right? They don't often, and they can be critically important to the flow in your field. You're losing the architecture, the definition of the trap. And trap definition, this is a picture from our software. It's, this is what faults actually look like in the field, and that's why we kind of built software that does that. When you kind of look around and you're kind of risking your areas around where you're working, you might think in terms of, okay, I've got a prospect over here next to this discovery that I like. I'll risk it in terms of charge, migrate, all the rest of it. Charge reservoir, they should be fairly low risk, really, if they're that close. But the seal and the trap, that all comes down to how well the trap has been defined. And if you look through the literature, and there is plenty, all of these dry hole analysis synopses all point to trap definition being the #1 reason for failure in dry wells. 79, they were dealing with 2D sections and paper maps, so they could be forgiven for making traps, but not great traps. But we've got beautiful 3D seismic data. We've got really good software that can map these things, and we're still not really paying it as much mind as maybe we should be. I can point you out, I'm just getting to wrap-up time. How long do I have left, Jim? Or 3? I can point you out a couple of publications. This one by Paul Whipp. He lovingly created this map of the Horda platform, the trawl field. This is about 50 by 70 kilometers, by the way. And when I look at that, I don't see slugs, and I don't despair. I see something aesthetically very pleasing, because I know the contours make sense where they close with the faults. Bob Krantz was one of the top guys at Conoco for a very long time. He's just retired, and Thomas Neely is his protege, really. And they created a very nice publication in the Headberg, which tells you how to interpret in 3D. It's a lovely piece of work. And Bob was top of his game for a very long time. And they use T7 because it's horses for courses, right? If you are using any of the software packages, you will start here and you will finish there. And if you use a different software package, you will start here and you will finish there. I'm not saying that one is better than the other, but they do different things and they have different workflows and they lead you different places and they grid things differently and they do things differently. In the business of trap definition, I would make the argument that you have to use a software system like T7. And, Cobra is something that we've published as well last year. This is the relinquishment map. It's just to kind of hammer home the point, right? Premier relinquished this on the basis of the discovery and the appraisal only showing kind of that much volume. Eon picked it up. They asked us to do a bit of fault seal analysis on it. And the first thing we do with most fault seal analysis projects are forget about the fault seal metrics. Forget about whether this fault sealed or not. This is what your trap looks like. Warts and all. This is what your trap looks like. And that's always value. Anyway, the fault here doesn't exist. And this fault here, which is an intact fault, is actually segmented. So, in fact, there was no reason to close the field there. And we did a framework fault seal analysis, which automatically looks at all the framework faults and picks the weakest point highest up to figure out where your spill is. And we figured that even when you take all of these faults into place, that's the oil-water contact. How long could you deliberate over all of these and never get near the answer? So in terms of risking, in terms of, when you're looking at prospectivity, you have to define the trap. You have to make sure that when you put a fault on, because when you put a fault on, it's a hard barrier. Everything on the other side has to close against it. If it's in the wrong place, all of this around it is wrong. It's not just where the fault is. If you put the fault there and everything changes. So it has to be done properly. And there are QCs, there are quantitative QCs that have been in the industry for a long time that can be easily applied by anyone and should be applied by all seismic interpreters, to our mind. Tried to cover a lot of ground, tried to cover a fair few of what's available in the 30th round. As you can see, more often than not, there's probably more upside to be had by just doing this properly. But you can't really use that equation without having gross rock volume in your mind in terms of the areal extent of the map. So, yeah, happy to chat at booth number 1 in the Combi Suite or answer any questions.